Question 1 of the WASSCE 2018 physics theory question, it says define strain. Okay, so what is strain? Now, strain is what? The relative distortion, okay, or change in shape or size of an object due to applied forces. Okay, so that's the meaning of strain. All right, is the relative what? Is the relative, these are the key words. Is the relative what? Change. You can put distortion, but I know most students will remember the word change. So it's the relative change in size of an object due to an applied what? Force. Okay, that's applied forces on the body. All right, and definitely I hope you know the formula for strain. Strain is the ratio of your extension, all right, your extension over your what? Original length. All right, that's the formula for strain, and it has no units. So the formula for strain is equal to extension over original what? Length, and it has no unit. Okay, so this is the answer for question what? A. All right, so when you're defining, make sure you put the key words, the key terms, all right, because that's what will give you the full mark. All right, so when you're defining, definitely put it is the relative change in size of an object due to applied forces or an applied force. All right, so this is the definition of what? Strain. You can see how it's stated here. Strain is the relative change in size of an object due to applied forces. And you can just quickly just state the formula for strain as strain is equal to extension over original length. So we also have question B here, and it says a rubber band is stretched to twice its original length. All right, calculate the strain on the rubber band. All right, a rubber band is stretched to twice its original length. Calculate the strain on the rubber band. So we have to know what our extension is and what our original length is. First of all, it has said the rubber band is stretched to twice its original length. Let's say you have a rubber band, then it's stretched to twice after applying a force. Twice is what? Original what? Length. So this is the original length, which is what? LO. Okay, this is you know, the letters used to represent this. E is for extension is E, and original length is LO. This O means what? Original length. So this is the original length. Then the next length is, that's the final length, is what? It's this from the statement. It says a rubber band is stretched to twice its original length. So the final length is what? 2 times what? LO. So we have 2 LO. So you can just state this. You know, this is a theory question, so you put your here. You know, it's very key for you also to number. So this is what? 1A, and this is what? 1B. Okay, you number your going on your answer sheet clearly for the examiner. All right, so you can state here. First of all, you just state the formula. Strain is equal to E over what? LO. Then you state original length from our question is equal to what? LO. Then the new length, and you know, you remember the extension. To get your extension is the final length, that's the new length minus what? The original length. Then the new length is equal to what? It says a rubber band is stretched to twice its original length, so it is what? 2 LO. So what is E? E is equal to what? 2 LO minus what? LO. Is that not it? Okay, so let's so we now put it into our formula here. So we have strain is equal to our E is now 2 LO minus what? LO over LO. Okay, so here don't make the mistake of making your new length as the extension, because that's some students do miss it by saying extension is just the new length. Extension is what? your new length minus what? The original length. So from here we have 2LO minus LO. That will give us what? An LO. Then we have divided by what? LO, and this would cancel out and we have 1. So our answer is what? 1. Remember, string doesn't have a unit, as I said from the beginning, so our answer is what? 1. So this is the solution to the first question of your WASSCE 2019 physics theory question. So you state your workings where you state your values. You can see the way I'm doing it. State your formula, the values you're given, then substitute those impute the values into your formula to find your answer. All right, question 2 of the WASSCE 2018 physics theory question. It says state 3 materials used for making optic fibers. All right, so state 3 materials used for making optic fibers, and so first of all, you must know what optical fibers are and where you use them. Okay, and the first thing that should come to your mind about fibers is its use in telecommunication. Where you see your computer networking, your base stations, you see a lot of fiber optics cables there. So that's where it's used. So what are the materials now that you use to make them? Okay, and one of the materials are what you have, what? Glass. Okay, you have glass. Glass is used in making fiber optics. So all you can do in stating your answer, you just write materials for making optical fiber, just according to how it is written. Okay, don't put it backwards like saying fiber optics. Okay, optical fibers, materials for making optical fiber, and you state them. It says state 3, but here I've given about 5. So these are the materials you use to make optical fiber. All right, sapphire, you use sapphire, silica, Teflon sheet, you use what? Polycarbonate, and also glass in very fine strands. Okay, so these are the materials that are used to make your optical fibers, the ones you see in even your just common computer cables. That's I think RJ45 cables. Those are also optical fibers are used in those cables. Okay, so from these 5 materials, so you just pick 3 that you're very comfortable with, that you quickly remember. And I know students will go for glass, silica, and polycarbonate. Okay, but don't forget that you can also use sapphire for making what? Optical fiber. All right, question 3 of the WASSCE 2018 physics theory question. It says name 3 classes of magnetic materials. All right, so there are 3 classes of magnetic materials. Materials are classified according to their nature of how to exhibit magnetism. All right, so several materials are being distributed into 3 classes, and these classes are, okay, you have your what? Diamagnetic, paramagnetic, and ferromagnetic. Okay, and ferromagnetic materials exhibit strong magnetism. All right, so where some example of ferromagnetic materials are your iron, okay, your nickel, okay, and some alloys like steel. Okay, so these are examples of ferromagnetic materials. They exhibit strong magnetism, and even without the presence of an external field or a magnetic field, they already exhibit little signs of magnetism. And for paramagnetic materials, you have examples such as your platinum, aluminium. Okay, and they are not as strong as your ferromagnetic. Okay, while your diamagnetic magnetic material classes, examples are your carbon and silver and mercury. Okay, so these are the examples of diamagnetic materials. All right, so the question says name name 3 classes of magnetic materials. So all you need to do is state this. Magnetic material classes are, okay, diamagnetic, paramagnetic, ferromagnetic. Don't make the mistake of just putting diamagnet and don't put the IC. You are going to get it wrong. Okay, so make sure you put your IC, diamagnetic. All right, you see, according to the statement here, magnetic material classes. So diamagnetic, paramagnetic, ferromagnetic. So don't do the mistake of just, you come here, you put paramagnet without putting the IC. You're going to lose marks if you don't put the IC. Question 4 of the WASSCE 2018 physics theory question. Question 4a says, what is an intrinsic semiconductor? Okay, I hope you know what a semiconductor is. Semiconductors are materials which their resistivity is between that of a conductor and what insulator. Okay, and for an intrinsic semiconductor, okay, it contains equal number of free electrons and holes. Okay, so for an intrinsic semiconductors, their electrical properties are not dependent on doping. And you know what doping is? That's introducing impurities to a semiconductor. Okay, so for an intrinsic semiconductor, it contains equal number of what free electrons and holes. Okay, now for part B, 4b says distinguish between p-type and n-type semiconductors. Okay, now the p-type and n-type semiconductors are when impurities are now added. So the p-type and n-type semiconductors are what? Extrinsic what? Semiconductors. Okay, so in case you are asked what's the difference between an intrinsic and extrinsic semiconductors? Intrinsic semiconductors, they contain equal number of free electrons and holes, and it's the electrical properties does not depend on it being doped. That's adding impurities to it. But for the extrinsic, you dope them. That's you add impurities to it. And for the extrinsic semiconductors, you have the p-type and the n-type semiconductors. Okay, now for the part B, it says distinguish between p-type and n-type. All right, so in your question, okay, I didn't even say how you write this down. So what is an intrinsic semiconductor? As stated here, an intrinsic semiconductor, just go straight to the point. In your theory part for your physics or your chemistry or your biology, don't write too much. Just the key terms. That's what the examiner is looking for. Your key points, the key terms should be stated. Contains equal number. This equal number of free electrons and holes. It's very key. So just state it that way. Now when it says, when you have a question, distinguish between this and this, you use a table, and we have a table here. All right, so this is our table. All right, this is digital table, but your own table should be with a pencil and paper. All right, so we have this here. So the difference to distinguish between p-type and n-type semiconductor. So we have it here. For the p-type semiconductor, it has what holes as what majority carriers of this. There's supposed to be an E here, electricity. While for the n-type, you can see p-type, the holes are the majority carriers, while for the n-type, your electrons are what? The majority carriers of what? Electricity. Now for the p-type, you have your impurity. That's the impurity you had. The dopant is what? Trivalent. All right, while for the n-type, the impurity is what? Pentavalent. Okay, there's a lot to explain on this, which will take a lot of time, but later in the future I will do a video by God's grace on semiconductors and explaining p-type, n-type, and how it is doped. All right, so for another difference is it is created by an acceptor impurity, while for the n-type it is what? Created by donor what? Impurity. And for the p-type, it what? Carries a net positive charge, because holes, it carries a net positive charge, while for the n-type it carries what? A negative positive charge, because of this n and this p. So this is easy for you to quickly remember. All right, this one I know most students will. This is the first one. It carries what? A net positive charge, and here it carries what? A net negative what? Charge. So this is the difference between a p-type and what? N-type what? Semiconductors. Okay, and you would notice that when you have let's say an exam, physics, like for this here 2018, when you go to the OBJ section, there are some questions in the theory. All right, in your OBJ section, you I don't know. Okay, But if you've written exams, there's always, there are always clues from your OBJ that would also help you in your theory section. All right, so look out for those little clues that you'd see in your OBJ section that would also help you out in your theory section. All right, so these are the differences between your p-type semiconductor and n-type semiconductor. So all you need to do is draw a table and list the difference. Don't start stating each one, okay? Like you just go here and say p-type, you say 1 it has this, 2 has this, 3 has this, 4 it has this. Then you bring this down without a table and say n-type. No, please draw a table. It says distinguish, draw a table, so it knows, the examiner knows what you're doing. All right, because if you bring this down and just state, you are just stating the properties of n-type semiconductor. But here you are told to what? Distinguish. So you draw a table to distinguish between p-type and n-type. Don't just list. All right, this is where students also fail a very this is also where students also lost a lot of marks. Don't list, draw a table, because it says distinguish between something and something, just like distinguishing between a girl and a boy, and you list features of a boy here, then you come down and list features. You are listing, you are not what? Differentiating or distinguishing. All right, so to distinguish, you draw a line, a table, okay, and distinguish between a girl and a boy, and it should be similar. Not that you write it has holes as majority carriers, then you come here for the n-type and say impurity is pentavalent. No, are you getting me? You can see here it has holes as majority carriers of electricity, while on the other side has electrons. We're talking here of majority carriers. This is the key, majority carrier. So what's the difference of p-type majority carrier from n-type majority carrier? All right, here you can see the key one is impurity. What is the impurity? Here it is trivalent, here it is pentavalent. Are you getting my point? Now here the third one, the key word here is created. It's created by what? An acceptor impurity. Here it is created by a donor impurity. Now here for the fourth one, what's the key word? Carries. It carries a net positive charge. While here, what does it carry? A negative charge, a net negative charge. So please follow this way of answering the question, what? Distinguish between something and another. All right, okay, so let's go on to the next question. Question 5 of the WASSCE 2018 physics theory question. It says a missile is projected so as to attain, this is attain, its maximum range. Okay, its maximum range. Calculate the maximum height attained if the initial velocity of projection is 200 what? Meters per second. Okay, initial velocity of projection is what? 200 meters per second. So when you say a missile, you should know that this is a projectile. All right, so this is projectile. So let's say we have this. All right, so a missile projected so as to attain its maximum range. Remember, what is your range? Let's say the projectile goes from here and lands somewhere, the missile. Okay, here our maximum range is the distance from where the missile was shot to where it landed. That's our range. Sorry, that's our range. Okay, range R. And our maximum height is the highest point, the highest height of the what? Missile, which is just here. Okay, so this is the maximum height. Let me abbreviate this, but for you, please write everything in full. Please write, or for you, please write everything in full. Okay, where our initial velocity, okay, is what u, and our angle theta is this way. All right, so it says so as to a missile is projected so as to attain its maximum range. Now, if any in projectile, if a missile or a warhead or a gun or a thrown bomb or a fired bullet, okay, or maybe in sport a kicked football, okay, so it's if it attains its maximum range, it means that theta would be what? Once you see anywhere in projectile and it says attain its maximum range, our theta will be equal to what? 45 what degrees. And remember, what's the formula to calculate? Well, I told here to calculate what? The maximum what? Height. The formula to calculate our maximum height is what? H is equal to what? U square sine square theta over what? 2g, where we're given our gravity as what? 10 meter per second mod square. All right, so this is the formula, and we already know that theta is what? 45 what degrees. We are told the initial velocity is what? 200 what? This is what? 200 what? Meter per second. Okay, so here we substitute the value, but for you, for your theory, for the theory section, all right, so but for you in answering, you draw your diagram, put your theta here, put it equal, label everything. Theta as what? 45 degrees. This is your maximum height, this is your range, this is your initial velocity. Okay, so you state here your theta, you say theta at maximum range is equal to what? Sorry, 45 what degrees. U is equal to what? 200 meter per what second. What else again do we need here? G is equal to what? 10 meter per second what square. State all this. Then definitely your formula, you should have stated your formula, maximum height is equal to this. So we substitute all this into this equation to get our what? Maximum what? Height. So what is U? U is what? 200. So we have 200 square times what? We have as this is 45, so we have sine 45 what? All square divided by what? 2 times what? 10. All right, so here when you punch in all these values in your calculator, you're going to get what? 1000 what? Meter. All right, so this is our maximum what? Height. H is equal to what? 1000 meters. So this is our answer. All right, so there are two key things to note here. You were not given theta, but from your statement it says a missile is projected so as to attain its maximum what? Range. At maximum range, your theta is equal to what? 45 degrees. Don't forget this, please. It's very key. In projectile, at maximum rate, sorry, at maximum range, your theta is equal to what? 45 what degrees. So, and remember your formulas, all your projectile formulas, please make sure you also put them at heart. So this is the formula for getting your maximum what? Height. And also don't you can also, drawing this diagram will also add you an additional mark, which will also be key. So draw your diagram to explain what's happened here in this in the statement. All right, state the values you have. First of all, write down your formula correctly, state the values you have, then impute them. All right, so this is how you answer question 5. So question 5, the answer is what? 1000 meter as your maximum height. That's the height from this peak here to the ground. Question 6 of the WASSCE 2018 physics theory question. It says a black body radiates maximum energy when its surface temperature T and corresponding wavelength lambda max are related by the equation lambda max T, this is T, equal to constant. Given the values of the constant and surface temperature as this and this respectively, calculate the frequency of the energy radiated. All right, so when you see questions related to wavelength, all right, always remember this formula. V is equal to what? F what? Lambda. All right, that's your wavelength. All right, always have this formula at heart. You will always apply it when you see questions corresponding to what? Wavelength. All right, and maybe radiation of a body, or a body radiating energy. Okay, so always keep this at that. So this is what F what lambda. All right, where F is what? F is your frequency, L is the wavelength, and V is what? Velocity. All right, so here now, let's write this down. It says okay, when its surface temperature T and corresponding wavelength are related by the equation this. So lambda max, sorry, this is lambda, which is wavelength, T is equal to what? Constant. Alright, given the values of constant as this and surface temperature as this, okay, as this, okay, so this is 2.9 times 10 raised to the power minus 3 meter Kelvin, and this is 57 Celsius. Okay, so you can see this, we have a difference in it. You can see this is Kelvin and this is what? Celsius. So we have to stay on one plane, on one unit. So it's always better you when in physics, it's always better to convert to what? Kelvin. Okay, so we have to convert this 57 Celsius to what? Kelvin. All right, so take notes now in your physics questions. Look, please pay attention to the units. Okay, you see some other questions again. Pay attention to the unit of measurement, all right, by the side of each number, and make sure you work with one unit in your question. The question might demand you to convert from one unit to another, all right, but you know, definitely the question is not going to tell you to do that. You have to read the question and know that you have to convert Celsius to what? Kelvin. Okay, so and you remember how to convert Celsius to Kelvin. I hope you know that. Now in getting our T, which is our temperature, first of all we need to find from here, I say calculate the frequency of the energy radiated. So definitely we need to find our what? Lambda max. And when we get our lambda, it's now easy for us to get our frequency by this equation. All right, where V will be the velocity of what? Light. Okay, so here we have here, to get our lambda max is equal to our constant over T. Okay, so we state here that constant from our question is equal to what? 2.9 times 10 raised to the power minus 3 meter Kelvin, and our T is equal to what? 57 what? Celsius, and to convert to Kelvin is what? And to convert to Kelvin is what? 57 plus what? 273. And what will this give us? 57 plus 273, that will give us what? 330 what? Kelvin. All right, so now we can put this into the equation. Let me just come down here. So lambda max is equal to our constant 2.9 times 10 raised to the power minus 3 mk over 330 k. Where this k will cancel out this k, you can see we have to cancel out. All right, if it was 57 Celsius, you can't cancel out. That's why we have to what? Convert Celsius to what? Kelvin. All right, so here we have, if we punch in our calculator, we're going to get what? 8.78 times 10 raised to the power minus 6 what? Meter. Wavelength is in what? Meter. All right, so these are max wavelength. So now to get our frequency, you now say, therefore remember that what? V is equal to what? F what? Lambda. All right, so this will now be what? V is equal to F lambda what? Max. So our F is equal to V over what? Lambda max. You know, you substitute. You know, to get make F the subject of formula, you divide both sides by what? Lambda max. That's why I said F is equal to this. And the same thing, that's what I also did here. To get your lambda max, you divide both sides by T. Okay, so please, if you don't, I always tell students the foundation of, in fact, change of subject of formula is key. Substituting is very key in maths, in physics, in chemistry, as a science student. It's key. You will use it till you graduate from school, even university. So it is key. If you don't understand change of subject of a formula, please go and watch the video and tell me. If you want me to do more videos for change of solved formula for you, I will do it, because it's very foundational, very key. You use it, you apply it everywhere to manipulate your formulas and your figures. Okay, so here, what's the velocity of light? We have to also state it. Velocity of light, V, you state it somewhere here. V is equal to what? 3.0 times what? 10 raised to the power 8 meter per second. Alright, so we now say F, we're supposed to have stated it somewhere close here, where we stated our values. Okay, so F is equal to what? 3.0 times what? 10 raised to the power 8 meter per second divided by, what is our answer here? 8.78 times 10 raised to the power minus what? 6 meter. Okay, and what do we have? When you punch in your calculator, we are going to have 3.4 times 10 raised to the power what? 13, and the unit of frequency is what? In what? Hertz. So 3.4 times 10 raised to the power 13 what? Hertz. In physics, please make sure, don't just write numbers without putting your unit. Always make sure you put your unit, because it takes a mark. Okay, at least half mark, so you don't lose that half. Alright, so this is our answer for this question. Your frequency is what? 3.4 times 10 raised to the power what? 13 Hertz. Question 7 of the WASSCE 2018 physics theory question. It says, what does the acronym LASER stand for? Okay, what does the acronym LASER stand for, and what is a laser? Okay, the acronym LASER stands for what? Light amplification by stimulated emission of what? Radiation. Okay, light amplification by stimulated emission of radiation. All right, that is the meaning of the word, the acronym word laser. All right, light amplification by what? Stimulated emission of radiation. That's the meaning of the acronym word laser. And what is a laser? A laser is a device that generates an intense beam of coherent monochromatic what? Light. Now the monochromatic light, okay, is light where the optical spectrum contains only a single optical frequency. Okay, I can't explain this in detail, but this is a laser. A laser is a device that what? Generates an intense beam of coherent monochromatic what? Light. And one of the uses of some of the uses of lasers are, in your let me see something. I want something closer to real life. Now, if you go to the supermarket like ShopRite and all that, what? There's a particular red, when you get to the counter where you pay for your items, a particular device that scans the barcodes of the item. Lady or gentleman at the counter will take your item, each one of them, to scan the barcodes, and you hear that noise, beep. It scans the barcode, then gives the price. All right, that device uses the laser technology. All right, so you use lasers in scanners. That's a scanner for a barcode. You also use it you can use it to also drill, to also cut items. That's why you see here is an intense beam. Okay, a device that generates an intense beam, so you can use it to drill, you can use it to cut. It's also used in medicine, also for some surgeries. All right, so and also in our computer system, what reads your data from your CD or yeah, from your disc players, your Blu-ray discs, is also a laser technology. A laser is used there. So these are some examples of where a laser is being used. All right, so it is a device that generates an intense beam of coherent monochromatic light, and the acronym laser means light amplification by stimulated emission of what? Radiation. Question 8 of the WASSCE 2018 physics theory question. Okay, in physics, your first compulsory part is from 1 to 7. Then the second part 2, is where you also pick some questions. All right, so we've just started part 2, which starts from question 8. All right, so this says what? Question 8 says define uniform acceleration. So what is uniform acceleration? All right, so uniform acceleration is the constant time rate of increase in what? Velocity. All right, remember your uniform acceleration is what? The constant what? Time rate of increase in velocity. All right, some students will just go ahead and say uniform acceleration is the rate of change of velocity with time. No, it is not. Okay, all right, so if you do that, you are going to lose a mark here, and a full 1 mark or 2 marks you would lose. But uniform acceleration is the constant time rate of increase in what? Velocity. The key word here, increase, has to be what? Put in your statement, in your definition. Increase, this is very key. Increase in what? Velocity. And also your constant here, constant what? Time what? Rate of increase in velocity. All right, now B says what are the forces forces act on a car in motion? List the A says horizontal forces and their direction, that's I, and I says what? Vertical forces and their direction. So let's say you have a car here. You have a car. So what are the forces now? For the horizontal forces, okay, this is horizontal and why this is vertical. This is horizontal, this is vertical, okay? For the horizontal forces, definitely what pushes the car forward is what? Your thrust, and that thrust comes from what? The engine, okay? That's what pushes the car forward, all right? Why the force that pushes it back, all right, is what is due to is drag, which is due to what? Friction. All right, that's what pushes it back. Friction from air resistance. A moving car, as you're moving, the wind, if you put your hands out of the car, you feel a force that pushes your hands back. That force is also felt by the car too, which is drag, air resistance. Okay, so but definitely the power of the engine in the car makes it to what? Move forward. That makes it to thrust forward. All right, so the horizontal forces are what? Your thrust and what? Your drag. So these are the horizontal forces, thrust and drag, where your thrust takes it what? Forward, while the drag takes it what? Backward. All right, so the vertical forces, the first vertical force here that brings it what? Downwards is your what? The weight of the car. Okay, and also the vertical forces that affects the car from not moving, that try to stop the car, is your what? Normal reactions. You have a normal reaction here on the tire to the surface of the road. If you don't have good tires, definitely you won't move, the car won't move. All right, because definitely there's a friction, there's a normal reaction on the surface of the road that would not want the car to what? Move. Okay, these are the forces that affects it. Your weight affects it, brings the car downward, while the normal reaction is what? Upward. Okay, so this is normal reaction. So these are the forces. So as we have here, for the horizontal force, your thrust is what? Forward. Since the question says list the forces act on a car in motion, a car that is moving, it says what? List what? The horizontal force and their direction. So the force, the horizontal thrust, what's the direction? Is forward. Then the other horizontal one is what? Drag, which I said is also friction. And what is the direction is what? It's taking it what? Backward. For your vertical forces, one of the force that acts on the car in motion is what? Your weight of the car, which is what? Downwards. And another force that acts on it on motion is your what? Normal reaction, which is what? Upward. Okay, so don't forget, please make sure you put normal reaction. Don't just put reaction alone. All right, you have to put your normal reaction. If not, you're going to lose a mark here. All right, you can lose like half mark. Make sure you put your normal, all right, with your reaction. So normal reaction. Okay, so here we have a question here. It says that's C. It says a car starts from rest and accelerates uniformly for 20 seconds. So we have here, this is you can see here is a velocity time graph. So let's draw it out here. I hope there will be enough space. Well, the velocity time graph. You can see here it says sketch a velocity time graph for the motion. So with your pencil and a ruler, okay, you label V. Okay, this is V, which is what? You can just put it in bracket. Your velocity V is what? Meter per what? Second. Where here is your what? Your time T, which is in what? Seconds. Alright? So a car starts from rest, and accelerates uniformly for 20 seconds. From rest, accelerate uniformly for 20 seconds. So on your time here, from here to here is what? 20 seconds. Okay, so let's say here is what? 20. To attain a speed of 25 meter per second. So it stops here, it attains a speed of what? Sorry, I'm supposed to break these lines here. Let's break. To attain a speed of what? 25 watts. So here 25 meter per second. You don't need to put meter per second here since it's already here. Alright. It maintains this speed for 30 seconds before decelerating uniformly to rest. Maintains the speed for 30 seconds. Let's say from here to here is 30. Okay. Before decelerating uniformly to rest. So at this point here, it decelerates to what? Rest. So from here to here is 30 seconds. So if this is 20, so 20 plus 30, so it means if we drop here, drop this line here, 20 plus 30 is what? What's 20 plus 30? That's 20 plus 30 is 50. Okay, that's 20 plus 30, 50. So we have 50 here. Okay, the total time for the journey is 60 seconds. See, it maintains this speed for 30 seconds, which we just interpreted here, before decelerating uniformly to rest. It says the total time for the journey is what? 60 seconds. That is from here to here is what? 60 seconds. Okay, and we know that from this point to here is 20, and from here to here is 30. So from here to here is what? 50. So if the total it says is what? 60, is that not in 60 seconds? So it means from here to here is what? 10 what? Seconds. Okay, so from here to here is 10 seconds. Why this is what? 60 seconds. All right, that's the total is what? 60 seconds. So sketch a velocity time graph for the motion. So this is the velocity time graph. All right, so you can also just label the graph so we can easily identify each point. So you can say this point is A, B. You can use any letter. You can say this point is A, B, C, but remember this is 0. Please make sure you put this here, 0. That's your origin, 0. Okay, A, B, C. All right, so this point is D, and this point is what? E. So this point is 0 or O. Okay, you can just make this O. All right, so O, A, B, C, D, E. Okay, O. All right, so the first question says use the graph to determine the total distance traveled by the car. The total distance traveled by the car. So the total distance traveled by the car. So the total distance traveled by the car is what? The area of what? The trapezium. All right, you know this shape here is a what? Trapezium. So the total distance traveled by the car is the area of this what? Shape. And what's the area of a trapezium? The area of a trapezium is what? Half bracket A plus B times what? The height, where A is this length from here to here, B is from here to here. Okay, where our height is from here to what? Here. So you know, I'm just managing the space here, but you have to state your workings. What do we do? What do I do? What do I do? So you have to state, let's say we state it here. Okay, we write down, we say total distance. After drawing your trapezium, you now go to II. II, you're going to state it. This II, okay, alpha. I alpha. All right, this is alpha. All right, I alpha. You say total distance traveled by car is equal to what? The area of the trapezium. Okay, which is equal to what? This. All right, so where you state your A, you're going to state it, list the values where A is equal to, what is A? A is from here to here, which is what? 20, and this is 50, so it is 50 minus 20, which is what? 30. What is B? B is what? From here to here, which is what? 60. All right, I hope you know from our graph here, from here to here, the total distance is what? 60. And what is our H? Our H is from here to here, which is what? 25. So let's put it into this equation. We have 1 over 2 bracket 30 plus 60 bracket what? 25. So what do we have here? This is 90 over 2. 90 over 2 is what? 45. Is that not it? 90 over 2 is 45. So 45 times what? 25. What would that give us? 45 times 25 will give us what? 1125 meter. All right. Okay. I just skipped, but for you, please don't jump this particular step. Please don't jump the particular step. Or let me just write it here. So we have here see 30 plus this is what? 90 over 2 times what? 25. When you cancel out here, we have 45. So we have 45 times 25, which is equal to 112 watt meter. So okay, now so B here. Okay, sorry, this is beta, which is II beta, says calculate what? The deceleration of the car. Now this is the deceleration when it decelerated from, you can see here, it maintains its speed for 30 seconds before decelerating uniformly to rest. So this is deceleration from here what? To here. And to get this particular part, which is what? BC. So this is the deceleration, that is what? BC, and BC here is a slope. Okay, so the deceleration of the car is the slope of what? BC. And to get the slope BC, it's just simply the ratio of what? BD over what? DC. So you just say, you state deceleration of the car is equal to, okay, I'm just managing the space here, please. Slope of, please bear with me, slope of what? BC. Okay, where it is equal to what? The slope of BC is BD over DC. Okay, and what is BD? BD is what? 25. And what is DC? DC is what? 10 over what? 10. So the 5 divided by 10. And what would that give us? That's what? 2.5 meter per second watt square. Okay, so your answer is what? 2.5 meter per second watt square. So this is the answer. Don't forget your unit of measurements was meter per second square. Okay, so this is our answer for this. All right, so please, I apologize for managing the space. I don't want to erase everything here, so this is still on motion, so I wouldn't want to erase everything here. All right, if it was different, if it was something else, I would have erased it. All right, so for the part B now, 8B, you can see this figure here. It said the figure illustrates force extension graph for a stretched spiral spring. Determine the work done on the spring. Okay, when you have, remember, when you see stretched spiral spring and force extension, remember your hooks and young modulus and all. Okay, but here we're told to what? Determine the work done on the spring. Now what's the formula for work done on a spring? In W. Okay, work done is equal to what? Half F what? E. That's half force times what? Your extension. That's the formula for work done on a spring. All right, so here so you state this, all right, so as your formula. Then what is F? Our force from this graph is what? 12 what? Newton. You write your Newton. Okay, this is the unit. All right, and what is our E? You know, it says a force extension. So our extension here, this is saying extension. You can see here this extension is in what? Centimeter, and not in what? Meter. Remember, in physics we always use your meter, all right, except you are told to use centimeter, but in physics it's always meter. So you can see your students would miss this. Let me erase this so you see what I'm talking about. You see this place clearly. Let me erase it. Sorry, I have to erase it. Okay. All right, so you see this is extension per what? Centimeter. This is the unit here. All right, so but you know in exam and all that, we just quickly rush without looking at the details. Your unit is very key. You can see this is the second question that we need to convert our units. If you don't, you miss the answer. All right, so you have to convert centimeter to what? Meter. And here it is what our extension is what? 0.5. So E is equal to what? 0.5 what? Centimeter. So you can see how important it is, all right, for you to state the values of your parameters, okay, before you just start solving, all right, because it will expose all those little traps that will make you lose marks. All right, so state the values of each of your parameters. You can see from here extension E, it will make you more detailed. You can see extension, and you see here is centimeter. So from here you can convert the centimeter to meter, and converting centimeter to meter, we do what? We divide by what? 100. All right, so we divide by what? 100. So from here our formula is what? Work is equal to 1/2 FE. So we have here 1/2 times what? 12 times 0.5 over 100. So when you punch in your calculator, this is here 1, this is here, in 12 we have 6. Punch in your calculator, and what are we going to have? We're going to have 0.03 joules. We're looking for work, okay? Energy and work have the same unit, so 0.03 what? Joules. So this is our answer for the work done on the spring, 0.03 joules. Question 9 of the WASSCE 2018 physics theory question. That's your WAEC physics theory exam. It says list 2 factors each that affect heat loss by radiation to convection. All right, so that is A. It said list 2 factors each that affect heat loss by radiation and convection. All right, for radiation you have surface, the area of the surface, okay, affects heat loss. All right, so we have them here. Okay, so you just state for the AI radiation surface area affects heat loss by radiation. Also the temperature also affects heat loss by radiation, and also the nature of the surface, all right, also affects heat loss by radiation. I hope you know what radiation is. It's the transfer of heat between two bodies by means of electromagnetic waves. Okay, so these are the factors that affect heat loss by radiation. Okay, I stated 3 here, but you're just asked to give only 2. All right, and when you're stating temperature, don't put change in temperature or temperature change. Just temperature affects what? Heat loss by radiation. Okay, so the surface area, the nature of the surface, and temperature. While for convection you have what? And I hope you know what convection is. Convection is the transfer of heat from a hotter region of a fluid to a colder region. All right, okay, through the actual movement of the fluid. Remember, like when you want to boil water, in your kettle and you drop on your stove, okay, the bottom of the pot of the kettle, the water at the bottom of the kettle will first get hot before the one on top of it. So you can see the fluid moves, the colder one goes down. All right, the colder water on top goes down and become what's hot. Before you know, everything in the kettle becomes hot and it boils. All right, so that's convection, transfer of heat, okay, in fluids. All right, so the factors that affect heat loss by convection is what? The nature, the type of the fluid, all right, the density of the fluid, and the thermal conductivity of the fluid, the exposed surface area, the heat specific heat capacity of the fluid. All right, so these are the factors that affect what? Heat loss by convection. So nature and type of fluid, density of fluid. All right, so you can just pick 2 out of all this. All right, so now question B, that's B, says state 2 factors that determine the quantity of heat in a body. So 2 factors, just 2 factors that determine the quantity of heat in the body. Now the first one is what? The heat capacity of the body. Okay, the heat capacity of the body is either heat or thermal capacity, okay, but you can just say heat capacity, it's okay. The heat capacity of the body, okay, will determine the quantity of heat in that body, and that the body could determine the quantity of heat in the body, and also the temperature. All right, so temperature will also determine the quantity of heat in a body. All right, and not temperature change. Please, students always put this temperature change. No, 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 you don't need to put the change there, okay, just temperature. All right, not temperature change. Temperature change means from a higher, from a maybe initial temperature to a new temperature. No, temperature, just temperature, okay, are the factors that determine the quantity of heat in a body. Now the question C, when you see, you have you noticed something that for your when we were doing motion in the car, we started from defining uniform acceleration and forces that act on the car, and a calculation under also motion. All right, so you can see that's the trend for the part 2 of the theory section. So here we are also looking at heat, and you can see here there's a calculation under what? Heat also. All right, so where this is it says, that's your 9C, says explain the statement the specific latent heat of vaporization of mercury is. Okay, we are not even yet, we've not, this is not the question, the calculation part yet, but it says explain the statement the specific latent heat of vaporization of mercury is this. We should explain this statement. Okay, so what does this mean? It means that 2.7 times 10 raised to the power 5, okay, joules per kg, okay, of heat energy is required to change 1 kg of mercury at its boiling point to vapor without temperature change. Are you getting it? Okay, now most students, what I find out is most students, you just go immediately and define specific latent heat of vaporization. But the question says explain the statement. So in explain the statement, you must state each parameters in your definition. It's good that you know the definition of the specific latent heat of vaporization. So if you know the definition, then you include what? The parameters of the statement, which is what? Mercury and 2.72 times 10 to the power 5 joules per kg. That's the heat. Okay, so this statement means that what? This value of heat energy is required or needed to change 1 kg. You remember specific, when you see specific, like specific heat capacity is 1 kg, but heat capacity is the total body. All right, so specific is 1 kg. All right, the heat energy needed to change 1 kg, all right, of mercury. You can see from our statement is mercury at its boiling point. You know, we're looking at vaporization, specifically latent heat of vaporization, at its boiling point to vapor, definitely without temperature change. All right, at a constant what? Temperature. So this is what this statement means. All right, it means this amount of energy is needed to change 1 kg of mercury at its boiling point to vapor without temperature change. So this is the answer for 9C. Now 9D says a jug of heat capacity 250 joules per kg contains water at what? 28 degrees Celsius. An electric heater of resistance 35 ohms connected to a 220 volt source is used to raise the temperature of water until it boils at 100 degrees Celsius in 4 minutes. All right, after another 5 minutes, 300 grams of water has evaporated. Assuming no heat is lost to the surroundings, calculate the I says mass of water in the jug before heating. I says specific latent heat of vaporization of steam. So where we are given the specific heat capacity of water as what this, okay? And remember that in heat transfer, the quantity of heat supplied is equal to the quantity of heat what gained, all right? Which also means the quantity of heat loss is equal to the quantity of heat what gained, all right? But here we have something supplying heat and something else gaining the heat. So you can see here it says a jug of heat capacity contains water. So the jug contains water, and an electric heater of resistance this is used to raise the temperature of the water until it boils. So from here we have here what is giving the heat? The electric heater. Okay, so we have what? Heat heat supplied by heater is equal to what? The heat gained, and heat is gained by water and also the vessel which is carrying the water, which is the jug. Okay, all right, so it's equal to heat gained by we can start with water or jug, anyone. You can say heat gained by jug plus heat gained by water. Okay, so the heat supplied by the heater is what? Equal to the heat gained by jug plus the heat gained by what? Water. All right, so and remember quantity of heat Q, okay, you're going to state this somewhere. Q is equal to what? MC bracket theta 2 minus what? Theta what? 1. Okay, so the quantity of heat supplied, so we have MC is equal to, this question I would need to erase all this. Okay, let me quickly just erase all this. All right, we need space here. We need space here because there are a lot of things I have to state down. We need space here. Okay, so I think we can now work now. So heat supplied by heater is equal to what? Heat gained by jug plus heat gained by what? Water. All right, so from here remember the heat supplied by heater is equal to what? The formula for the heat supplied, quantity of heat supplied by heater. Remember this is a general formula for what? Your quantity of heat. But when it comes to electricity, Q is equal to what? IV what? T. Is that not it? IVT. So where I is your current, V is your what? Voltage, and T is your what? Time. But here from our statement here, an electric heater of resistance, we're only giving resistance and what? Voltage. So we can substitute we're not given the current, and remember that V is equal to what? IR. Is that not it? So where our I will be equal to what? V over R. That I will be equal to V over R. So we can take out this I from here since we're not given current. So in taking out the I from here, okay. In your answer sheet, please solve them together. Okay, so you just state here V is equal to what? IR, where I is equal to V over R. So putting in I into here, Q will now be equal to what? V over R times what? VT, which will be equal to what? V square T over what? R. So heat supplied by the heater will be what? V square T over R, since we have our R as 35, V as this, and we also have our time, 4 minutes. Okay, so we have here let me come here. So we have V squared T over R is equal to heat gained by jug is what? MJ CJ bracket what? Theta 2 minus what? Theta 1. Okay, all right, plus the heat gained by water is what? MW CW. I'm putting this W as what? Mass of water. You see here the specific capacity of what? Water bracket what? The final temperature minus what? The initial what? Temperature. Okay, which is the same. All right. Okay, so this is the formula we're going to use. Make sure this is stated clearly in your answer sheet. All right. So when you have this, now let us now state the parameters and their values. So from here our V is given as what? 220 what volts. Okay, our T is given as what? This is, it say is used to raise it until it boils at what? Our final temperature 100 degrees Celsius in what? 4 minutes. So our final temperature here is what? The final temperature 100 degrees at what? 4 minutes. Our time is what? 4 minutes. Remember, we can't work with minutes, we have to work with what? Seconds. So we have to convert this 4 minutes to seconds. In converting 4 minutes to seconds, we have what? 4 times what? 60. Okay, which is what? 240 what? Seconds. Alright, our R is given as what? 35 what? Ohms. Then equal to MJCJ. From here, that's the mass of the jug and the specific heat capacity of the jug. But here you can see that a jug of heat capacity, we've been given our M what? C. Remember, all right, the difference between specific heat capacity and heat capacity, you really need to know it. All right, your heat capacity has its own formula. Heat capacity, which is written as what? Your big C, is equal to the mass, whatever you the heat capacity you're looking for, mass times what? The specific capacity of the what? Substance. Okay, this is your what? Heat capacity. While your specific capacity, which is this small c, okay, is a standard for each material. Like here we've been given the specific heat capacity of water is what? This. All right, so you can also be given the specific capacity of maybe mercury as what? Something. All right, so this is the formula for finding your what? Heat capacity. But for quantity of heat, which is what? Q is equal to what? MC, then your change in what? Temperature, which is what? θ2 minus what? θ1. That is your Q. Why this is your what? Heat capacity. Make sure you understand these two formulas and don't confuse them. All right, this is your heat capacity, this is your what? Quantity of what? Heat. Okay, so from here we have been given our what? The heat capacity of the jug as what? 250. So our MJCJ is what? The heat capacity, which is what? 250. So you're going to state here MJ, which is the mass of the jug, and specific capacity of the jug together is what? 250. Our θ2 is definitely 100, and our θ1, say a jug of heat capacity, this contains water at what? 28 what? Celsius. So θ1 is equal to what? 28 what? Celsius. All right, so from here also our MW, that is what we're looking for. We're looking for what? Mass of the water in the jug before heating, so which is what? MW. This is our unknown. And our CW, which is what? The specific heat capacity of water, is what? 4,200. So CW is equal to what? 4,200. All right, where θ2 and θ1 is still what? 100 and what? 28 degrees Celsius. All right, so let's now put in all these values. So what's our V square, which we have what? 220 squared times what? Our T is what? In seconds, 240 seconds, over what? Our R is what? 35, equal to what? Our MJ is what? 250, bracket θ1 minus θ2 minus θ, that's 100 minus 28, bracket plus, we're looking for our MW, times 4,200, bracket what? 100 minus 28. Okay, from here when we punch in our calculator with all this, we're going to have 331,885.7. okay, for this part. Okay, 250, 100 minus 28 will give us what? 72. 250 times this will give us what? 18,000, plus we have our MW is what we're looking for, and this is 72. So this times this will give us what? 302,400. Okay, so from here what do? We take this here, right? If we take this 18,000 here, we're going to subtract, so we have 331,885.7 minus 18,000, all right, equal to what? MW. This is MW times this, which will be what? 3. Let's write it properly. 302400 MW. That's our mass of water. Okay, where we have to divide both sides by this. All right, so divide by 302400. So divide also 302400. So this will cancel out this. So when you subtract this from this and divide by this, we're going to get what? MW is equal to what? 1.03798 kg. That's the mass. All right, and if you're not given the decimal place to change to, always I think I said it before that you should do 2 significant figures, but I think you should increase more, or I said 2 decimal place, but it's always good you have higher decimal places. So let's do 3 decimal places. So to approximate this to 3 decimal places, we have, from your decimal points we count 1, 2, 3. Can we approximate? Yes, we can approximate. So we have a 1.038 what? Kg. So this is the mass of what? The water. So this is our answer, all right, for I1. Now I2 says find the what? Specific latent heat of vaporization of steam. So how do we get this now? So from this, it said it boils at what? 100 degrees Celsius in 4 minutes. It now says after another 5 minutes, 300 grams of water has what? Evaporated. So specific latent heat means what? When it what? Evaporates. Vaporization, all right, of steam. So after another, so we're going to get our values from this, from here, from this full stop. After another 5 minutes, 300 grams of water has what? Evaporated. And remember the formula for finding the quantity of heat, okay, for your specific and latent heat of vaporization. Q is equal to what? M what? L. Okay, where this is a mass and L is what? The specific latent heat of what? Vaporization. All right, so what do we do here? So it means that the heat supplied by the heater will be equal to what? The heat gained by the steam. Okay, that's to convert water to what? Steam. That's 300 grams of water what? Evaporated. So we have here, where do we do this? Where do we do this? Let me erase this. Okay, let's see if we can use here. Okay, so we have here, we say heat supplied by heater is equal to what? Heat gained by steam. Okay, where the heat supplied by the heater is what? Remember our formula is what? V squared T over R is equal to heat gained by the steam is what? M what? L. Okay, ML. All right. Okay, so where we're looking for the specific latent heat of vaporization of steam, which is what? L what? S. That's what we're looking for. And remember, it says after another what? 5 minutes. So our new time here now will be what? 5. Okay, so it says 5 minutes. So as we converted, you know, here we converted minutes to seconds by just multiplying by 60. So our V is still what? 220. So we have what? 220 times what? 220 squared times what? 5 times what? 60 over what? 35 equal to our M, which is what? The mass of the steam. It says what? 300 grams of water has what? Evaporated. So this is the mass of what? The steam, 300 grams. All right, you can see here this is gram, and we've been all along it has been what? Kilograms. That's not a kilogram. So we have to convert this gram to what? Kilogram. In converting gram to kilogram, we divide by what? 1000. Is that not it? So we have what? 300 divided by what? 1000 times what? L. L what? S. That's the vaporization or latent heat of vaporization of steam. That's what we're looking for. So let us make this the subject of formula. So what do we have? LS will be equal to, you have to take this up and bring this down. We have 220 squared times 5 times 60 to be now times, we add times 1000, then divide by what? We have 35, then times what? 300. And when you punch in your calculator, we are going to have a specific latent heat of vaporization of steam as what? LS will be equal to what? 1.38 times what? 10 raised to the power 6 joules per what? Kg. Okay, so this is our answer. Alright, when you punch in your calculator for this, we're going to have 1.38 times 10 raised to the power 6 joules per kg. Okay, so we are done with question 9. Alright, so the specific latent heat of vaporization of steam is what it is. So you state this down. Alright, so I hope you follow me through this particular question. Alright, if you have any questions, please feel free to drop it in the comment section. Alright, let's move to the next question, question 10. Question 10 of the WASSCE 2018 physics theory question, that's your WAEC physics theory past questions. It says define diffraction. Diffraction is just simply the bending or spreading of a wave round an obstacle or as it passes through an opening. Okay, let's say you have an opening like this, alright, and you have a wave passing through here. When it passes through this small opening, okay, the wave tends to what? Bend. Alright, you see the waves bending like this. This is what diffraction. Alright, okay, so question 10b, 10bi, it says explain what critical angle. What is what critical angle? Alright, I have two definitions here of critical angle. Okay, but in picking any of them, just make sure you draw the diagram. Alright, you don't draw the diagram. And critical angles happens from a denser medium to a less dense medium. Okay, let's say from a denser medium like glass towards air. So you have something like this. Okay, you draw your normal, you write here denser medium, or you can put glass and less dense medium, which can be air. Okay, so you have an incident ray. Okay, before we draw this, okay, first of all, what's a critical angle? All right, a critical angle is the angle of incidence in which the angle of refraction is what? 90. Okay, so you have this, and it's always from a denser medium to a less dense medium. So when you have an angle of incidence like this, okay, this is the angle of incidence. All right, the angle of refraction will be what? 90 degree. Okay, where r is what? 90 degree. All right, so the critical angle is what? The angle of incidence when the refracted angle is what? 90 degrees. So when the ray refracts at an angle 90 degrees, which means also being totally internally reflected, okay, the angle of the incidence at that particular point is what? The critical angle. All right, and not some students mistake that the critical angle as what? The refracted angle, which is no. A critical angle is the angle of incidence when the refracted angle is what? 90 degrees, and is from a denser medium to a what? Less dense medium. So when you are defining this, try to just draw a diagram. All right, any definition, if you have a diagram, just try to draw a diagram. It actually adds a mark. Even if it's half mark, it's also going to do something. Let's say you miss a particular key term in your definition, your diagram can actually help you in making up for it. You know, the examiner needs to know that you have at least 80% of the idea of what you are trying to define. All right, so this is what a critical angle. It says it's a minimum angle of incidence above which a ray passing through passing from a denser medium to a less denser medium will be totally internally reflected. Okay, totally internally reflected means here the angle of refraction is what? 90 degrees. Okay, or it says it is the angle of incidence in the dense medium for which the angle of refraction in the less dense medium is what? 90 degrees. All right, I think this definition is quite straightforward. So critical angle is the angle of incidence in the dense medium. Okay, angle of incidence in the dense medium for which the angle of refraction in a less dense medium is what? 90 degree. So when the angle of refraction in a less dense medium is 90 degrees, the angle of incidence is what? Your critical angle. All right, so now we have a question here. It says BII says the diagram here illustrates a ray of light passing through a rectangular transparent plastic block. Okay, rectangular transparent plastic block. Alpha says determine the value of the critical angle. All right, so you can see here this is a rectangular transparent plastic block to air. So this is a dense medium, and this upper one is what? A less dense medium. And this is, I'm sorry I forgot, this is our normal, and this is a normal. Okay, where this is the plane. Okay, so here this is dense medium and less dense medium. Okay, so if this is from here, this is the angle, this is angle 45, but always know that your incident angle is always the angle to the normal. All right, it's always the angle to the normal. So the incident angle here is from here to here. And to know that this is a critical angle, we can see here that the refracted ray here, okay, the refracted, and we can see here that the refracted angle here is what? 90. Is that not it? So it means that this place is what? The critical angle. And to get this angle is just simply what? 90 minus what? 44. So you just state critical angle. I want to just state it somewhere here. Let's manage this space to solve this question. Okay, we just state here critical angle, as critical angle is equal to what? 90 minus what? 44, which will be equal to what? 46 degrees. So these are critical angle. So beta says calculate the refractive index of the block. Okay, calculate the refractive index of the block. Okay, for this, from a dense medium to a less dense medium, our refractive index n is equal to 1 over sine c, where c is what? The critical what? Angle. Is that not it? So we have here is equal to what? N is equal to what? 1 over, let me write it here, n 1 over sine c. So it's equal to what? 1 over what? Sine 46 degrees. Okay, so and what is 46 sine 46 degree? That's 1 divided by, or when we just compute this, when you compute this on your calculator, 1 divided by sine 46 degrees, you're going to have what? 1.39. So this is our refractive index of the block. Okay, so this is the answer. All right, okay, and remember, please, I just solved this in just short form. Please make sure you state all your workings and put down all your values. The value of c is equal to 46 degrees and all. Okay, so this is the answer for beta, 1.39. Now for our part C, 10C, it says a pipe closed at one end has fundamental frequency of 200 Hz. The frequency of the first overtone of the closed pipe is equal to the frequency of the first overtone of an open pipe. Calculate II, the fundamental frequency of the open pipe, II, the length of the closed pipe, III, the length of the open pipe. The speed of sound in air is what? This. Okay, now it says a pipe closed at one end has fundamental frequency of what? 200 Hz. That's This is the closed pipe, okay? Closed pipe fundamental frequency, that is FO. So you state it, closed pipe fundamental frequency. Okay, let's just show you. Let us write it in. FO is equal to what? 200 what? Hertz. So it now says the frequency of the first overtone of the closed pipe is equal to the frequency of the first overtone of an open pipe. I hope you know the overtone of the first overtone of the closed pipe and that of an open pipe. Okay, you should always know this, all right? And remember that when it comes to your closed pipe, okay, your closed pipe is what? 3 watts, 3 watt FO. That's 3 times the fundamental watt frequency. Okay, so here the first overtone of closed pipe is equal to what? 3 FO. Okay, and the first overtone of open pipe is equal to what? 2 FO. Okay, there are details on how to get this. Okay, I can't start explaining that in this video, but in a proper video where I explain the introduction to topic, it will be explained. Okay, so it says what? The frequency of the first overtone of the closed pipe is equal to the frequency of the first overtone of an open pipe. So it means let's write this here. It means 3 FO is equal to what? 2 FO. Is that not it? Okay, so from here it is easy now for us to get what? The fundamental frequency of what? The open pipe. So from here, since the question that the frequency of the first overtone of the closed pipe is equal to the frequency of the first overtone of the open pipe, since they are equal, so it is now easy for us to get the fundamental frequency of the open pipe, since we have the fundamental frequency of what? The closed pipe as what? 200. So where 3 FO is what? Our first overtone. Okay, so FO for the closed pipe, okay, it's what? Is what? 200. So we have 3 times what? 200 equal to 2. This is the FO, fundamental frequency of what? Our open pipe, which is what we're looking for. Okay, you can just say FO for how do we differentiate them? Okay, let's just say P, open, so it lists open. Okay, so here to get this FO, we divide both sides by 2. So here we have 2 here, 1, 2 here, we have how many times? 100. So we have 3 times 100. These 2 will cancel out these 2. So FO for open pipe, for open, it will be equal to what? 300 Hertz. Okay, so since we've gotten the fundamental frequency of our open pipe due to this statement here, okay, where we substituted, all right, be watchful when substituting, okay, so you don't make a mistake. All right, so we've gotten our I. This is our I. So for our I now, it says the length of the closed pipe. How do we find the length of the closed pipe? So to get the length of the closed pipe, where remember that the first length of the closed pipe is what? L is equal to what? Lambda over what? 4. Okay, lambda is equal to what? 4 what? L. Okay, and remember that V is equal to what? F what? Lambda. Okay, so here this is 4L, sorry. Okay, so from here, if V is equal to F lambda, F is equal to what? V over what? Lambda. Okay, so where we substitute our lambda as what? 4L. So our fundamental frequency FO is equal to what? It will be what? V over what? 4 what? L. Okay, this is the fundamental frequency. All right, this is the first length of a closed pipe. Okay, which is what? L is equal to lambda over 4, where lambda, that's our wavelength, is equal to what? 4L. Okay, and remember that V is equal to what? F what? Lambda. So F will be what? V. That will bring the lambda down. That's a wavelength down. F will be what? V over what? Lambda. And substituting the value of lambda, which is what? 4 over L, we put it down here. That's how we got F is equal to what? V over what? 4L. So from here we can get our length of the closed pipe. Since we know our FO and we know our V as what? 330. Okay, so here, making L the subject of the formula, what are we going to have? L will go up and F will come down here. So we have here L is equal to what? Let me write this here. Okay, so it's equal to what? From here, making L the subject of the formula, we have L is equal to V over FO4. And what would that give us? That is V is 330 over a fundamental frequency of the closed pipe is what? 200 times 4. Okay, so when we punch in our calculator, what are we going to have here? We are going to have 0.4125 meter. Okay, that's the length of the closed pipe. Now the third one, I says the length of the open pipe. So what's the length of the open pipe? Definitely the fundamental frequency formula for an open pipe is what? FO is equal to what? V over what? 2L. Alright, where for an open pipe, L is equal to what? The first length is equal to L is equal to what? Your lambda over what? 2. Okay, and when you do the same substitution like I did, we are going to have what? FO is equal to V over what? 2L. Where here, making L the subject of formula, we have L is equal to what? V over 2 what? FO. So here we have our V is 330 over 2, and what's our FO? The fundamental frequency of the open pipe. We found it here. Where is it? 300. Okay, this should be I. Okay, found it here as what? 300 hertz. So times what? 300. So what would this give us? 330 times divided by this. When we punch in our calculator, we're going to have 0.55 meter. Okay, so this is our answer for this and this. All right, so I'm going to do a video on closed pipe and explain in detail. But it's always good. This question always comes out in your WAEC, either in your OBJ or in your theory section. Your open pipe, closed pipe, the questions always come out. Okay, because it confuses students a lot. All right, and what confuses students is just the what's the first overtone of the closed pipe, the second overtone, and all that. Okay, and also in substituting your value for V, F lambda. Okay, getting your fundamental frequency. That's the major thing that confuses students. But with this, just know what your first overtone is, your second overtone is. All right. For the first overtone of a closed pipe, you will notice that is an odd multiple. Like you have you have first of all your FO. All right. After your FO, you have your 3FO. The second overtone is your 5FO, and so on, odd multiples. Okay, but for your closed pipe, they're just normal multiples like 2FO, 3FO. 3FO is the second overtone, 4FO is the third overtone, and so on and so forth. Okay, question 11 of the WASSCE 2018 physics theory question. That's your WAEC physics theory past question. It says, question A says define I, which is what? Reactance. And what is reactance? Reactance is what? The opposition offered by an AC, that's an alternate circuit, by an inductor or capacitor. Okay, so that's what your reactance. An opposition, what is the opposition offered to an AC circuit? Okay, that's an AC alternating circuit by an inductor or capacitor. All right, so you can see this keyword opposition offered to an AC circuit, all right, by an inductor or capacitor. All right, this is the meaning of what? Reactance. Now for your I, impedance, what's the impedance Impedance is what? Is the overall opposition offered to an AC in a what? A resistant inductor or resistant capacitor or a resistant inductor capacitor what? Circuit. Alright, you must state all this. Alright, you don't just write impedance is the overall opposition offered by circuit elements like a resistor, inductor or capacitor. You must state the type of circuit it is. Okay, so impedance is the what? Overall opposition offered to an AC in an what? Resistant inductor or resistant capacitor or resistant inductor capacitor what? Circuit. Okay, the overall what? Opposition. You can see reactance is what? The opposition offered to an AC by just an inductor and capacitor, no what? Resistor. Alright, while impedance is what? The overall opposition offered to an AC in this circuit in a resistant inductor or resistant capacitor or resistant inductor capacitor what? Circuit. So that's the meaning of what? Impedance. Now for the next question, it says the diagram here illustrates an AC generator. Okay, this is an AC generator. When the coil is rotated, an EMF is induced in the coil. Explain why an EMF is induced. Okay, an EMF is induced as the coil, when the coil rotates, these are two magnets here, strong magnets here. As the coil rotates, it cuts across what? The magnetic flux lines. That's how the EMF is what? Induced. Okay, so the EMF is induced because the coil cuts magnetic flux or what? The magnetic what? Lines of what? Force. Okay, you can just say the EMF is induced because the coil cuts magnetic what? Flux lines of what? Force. Okay, alright, so I says state the purpose of the slip rings. That's this rings here. Now the purpose of this the slip rings are to do what? To ensure that the direction of current is reversed in each half of the rotation of the coil. Alright, is to ensure that the direction of the current is what? Reversed in each half of the rotation of the coil. Okay, where you see the next statement is also related to this question. It says name and state the law used to determine the direction of the induced current. The law used to determine the direction of the induced current is what? Lenz's law. Okay, it says state it, name it, which is what? Lenz's law, then state it. It states that the direction of the induced current is such as to oppose the change producing it. Are you getting me? Alright, so if the change producing the induced current is this way, the induced current will be what? The other way. Okay, that is Lenz's law. Alright, question IV says state two ways to increase the induced EMF. Okay, there are several ways to increase induced EMF, like increasing the rotation of the coil, alright, having a stronger magnet, alright, and you know, your core should be laminated. That's having an efficient core design. Okay, these are some here. It says here increase the speed of rotation, increase the number of turns in the coil, increase the diameter of the coil, efficient core design. So these are ways to increase the what? Induced EMF. You are just told to state two ways here, but these are four ways to increase the induced EMF. Okay, produced. Alright, okay, now question C says a lamp is rated 12 volts 6 watts. Calculate the amount of energy transformed by the lamp in 5 minutes. In 5 minutes, you can see this is minutes. We have to convert this to what? Seconds. Okay, in whatever formula we're using. So we're finding energy, and we have power, and we have voltage. Okay, remember what is energy? Energy is equal to what? Energy is equal to what? Power times what? Time. Is that not it? Power times time. Alright, so here we're looking for the amount of energy transformed by the what? Lamp in what? 5 minutes. So here we have, what is our power? A lamp is rated 12 volts 6 watts. Remember, power is measured in what? Watts. So this is our power here. We have 6. Okay, so you're going to state it. P is equal to what? 6 watts. Alright, T is equal to, that's your time, is equal to what? 5 minutes. Converting to seconds is what? 5 times what? 60. Okay, so we have times what? 5 times what? 60. So when we multiply all this, 6 times 5 times 600, what are we going to have? We're going to have 1,800 what? Joules. So these are answer. As I've said earlier on, don't just punch in your calculator the figures, just check that you have your units right. Okay, so this is 5 minutes, which you have to convert to seconds, and in converting to seconds you just multiply by what? 60. So we have our answer. The energy, amount of energy transformed by the lamp is what? 1,800 what? Joules. Question 12 of the WASSCE 2018 Physics Theory Past question. That's a WAEC Physics Theory Past question. This is a final question here. Alright, it says that 12A says define binding energy in an atom. And what is binding energy? It's just simply the minimum energy required to separate the nucleons of an atom. Alright, so let's see that definition here. It says what? Binding energy is the minimum energy required to separate the nucleons of an atom. Alright, so that's binding energy. Now, 12B says list 3 evidence to support the claim that X-rays are electromagnetic waves. Okay, any electromagnetic wave, first of all, it must travel in a vacuum. Alright, so that's one evidence to support the claims that X-rays are electromagnetic waves. Another one is that it travels with the speed of light. Alright, and another one is it's not affected by electric or magnetic fields, and it can be polarized. Alright, so these are evidences to support the claim that X-rays are electromagnetic waves. Now C says list 3 peaceful uses of nuclear energy. Alright, one of the uses of nuclear energy is to generate electricity. Okay, and also it's used in treatment of cancer, and let me see what are the lists here, and also to power submarines and rockets. Okay, say to generate electricity, treatment of tumor or cancer treatment, and to power submarines and rockets. Now we have a question here to calculate. It says that's 12D says light of wavelength 0.5 times 10 to the power minus 7 meter is incident on a metal, resulting in the emission of photoelectrons. Okay, alright, so when I always say when you see wavelength, just let this formula be with you. Let this formula be in your heart. V is equal to what? F lambda. You must always use it. Okay, alright. If the work function of the metal is this 3.0 times 10 raised to the power minus 9 joules, calculate I. Says the frequency of the incident light, II, energy of the incident light, III, energy of the photoelectrons. Okay, so let's start with I. It says the frequency of the incident light. So from here we have V is equal to F lambda. So we have to look for the frequency of the incident light. So from here V is equal to that's the speed of light, 3.0 times 10 raised to the power 8 meter per second. F, that's what we're looking for, and our lambda, we're given the wavelength of this 4.5 times 10 raised to the power minus 7 meter. Okay, so where F, from here you substitute, F is equal to V over lambda. So from here F is equal to our V is 3.0 times 10 raised to the power 8 divided by 4.5 times, is the point here, 10 raised to the power minus 7. When we punch in our calculator, we should have here 6.67 times 10 raised to the power 14 hertz. Okay, so this is our answer for I. Now I says the energy of the incident light. Now the formula to find the energy of the light is what? E is equal to what? H what? F, where H is what? Planck's what? Constant. So here we already know the frequency of what? The light, which is what? 6.67. So we have Planck's constant is this. So we have 6.6 times 10 raised to the power minus 34 times what? 6.67 times 10 raised to the power what? 14. Alright, so when punching our calculator, we should have 4.4 times 10 raised to the power minus what? 19 what? Joules. You know, we're looking for energy, so it has to be what? Joules. Alright, so here III says the energy of what? The photons. Okay, the energy of the photon, which is what? The kinetic energy of the photon, is equal to what? The energy of the incident light minus the what? Work function. Okay, so we're looking for the energy of the photo what? Electrons is what? The energy of the incident light, which we've gotten as this, alright, minus the work function, which has the work function as a result of the emission of photo what? Electrons. Okay, so that's this value. Alright, so the energy of the photoelectrons is what? Is definitely what? The energy of the incident light minus what? The work function. So here we have, what's the energy of the incident light? Is this 4.4 times what? 10 raised to the power minus 19 joules minus our work function is what? 3.0 times what? 10 raised to the power what? So this will be 10 raised to the power minus what's this here? That's this should be 10 raised to the power minus 19. Okay, this should be 10 raised to the power minus 19. Okay, so 10 raised to the power minus what? 19 what? Joules. Okay, so this minus this will give us what? A 1.4 times 10 raised to the power what? Minus 19 joules. So this is the what? Answer. Alright, so this is the energy of what? The photoelectron. So this is our final what? Answer. Okay, so thank you so much for staying tuned to the end of this video. Alright, so please give this video a thumbs up, share this video to your friends, family and loved ones. Any questions you need to ask, please drop your comments in the comment section below. And don't forget, Jesus Christ is coming soon. Give your life to Christ, for He is the way, He is the truth, and He is the life, and is calling unto you today. Alright, so thank you for staying tuned from DTW Tutorials. You are destined to win in your forthcoming exam and also in life. Alright, thank you, and see you in our next video. Bye.